Good morning, everyone. Thanks for being here. So this is the first talk of the morning. I need to warm up. I'm still shy, but I hope at in the middle of the presentation here, I will be nicer. So today we'll talk about prompt engineering. Okay, we're gonna be together until 10:30, and after that we're gonna have a break and probably have some coffee and etc. So we'll be talking about this comprehensive overview of what prompt engineering is, what are the techniques behind it, and what are also the best practice and the impact on building FMware. Okay, so I'm Filipe, Cogo, and I work at Huawei Canada with lots of my colleagues are here. So quick outline of this talk. So be basically giving you some very basic concepts around prompts. Okay, so prompts are the way you talk with the foundation models, and I just want to show you an example. It's something very simple. I'll be also talking about some prompt engineering techniques, and I will then talk about sampling and decoding. So there is thanks Gopi. There is something between the last layer of the foundation model and what you actually see. Okay, this is the decoder, and the decoder do some sampling, and I will be talking about this. I will then talk about a problem with prompting foundation models that affect software engineering a lot, which is the fragility of prompts. And then I will go more into how we need to manage those prompts. We need to version these prompts. We need to, basically what we do with libraries, we also need to do with prompts. And I will wrap up my talk talking about prompt compilers. That's what we see. We'll be actually taking over the manual editing of prompts. We don't think that's sustainable to have someone in the loop always changing these prompts. Okay, so let me start with the more basic concepts. So prompts are the way we instruct foundation models. Okay? That's the interface between the foundation model and someone, or the developer or the software maker. Okay, and it will somehow replace or complement or interact with traditional programming code. Actually, at the end of this talk today, I hope I can show that there is a lot of parallels between programming languages and prompts, actually. Okay? And prompts allows us to do something called in-context learning. So we basically do not need to retrain the model to teach the model something new. We can use the prompts to, give the foundation model some training data, and this is called in-context learning. Okay, so that will enable new capabilities because you are teaching the model something new. Okay, and a prompt actually it's a structured element. Okay, there is a lot of parts in a prompt. And I will discuss now what these parts are, okay? And so when you look at a prompt, okay, there are basically two big components with subcomponents inside it, okay? So these components can be task related, so related to the task that you are asking the foundation model to perform, or they can be context related. So sometimes you are giving what we call context to the foundation model, which could be some knowledge that you retrieved from a database, okay? Can be some examples that we're giving to the model such that it follows these examples during the generation and things like that, okay? So when you look at the task-related components, we have basically instruction, okay? That describes what completion task the model should perform. So you really instruct the model to generate some certain content. Okay. We have constraints that set some boundaries for the contents that the model can generate. So you can literally ask the model, do not generate these certain words, or make sure that you generate the output, okay, containing some words or something like that. Okay, so you constrain the output somehow. And you can also have some definition, okay, of the output format. This is very important when you are going to parse, okay, the output of the foundation model to reuse or to pass along a pipeline of operations. And then you need to define what this output format is, such that you can parse it. And the ones related to the context, we can highlight here the knowledge, okay, that will provide the model with some background information. So, sometimes these models are trained like months ago, and it's very hard to retrain them. So what you can do is just get some factual information that it's up to date. Probably this is done, very likely this is done by retrieving from a database, okay? And you just append this to the prompt, and now the model, this knowledge is prior to what the model will generate, okay? And you can have examples, few short examples that will provide the model some instance of what you expect the model to generate. And it's very common also to have personas, which are basically, stereotypes, identities that you give to the model. So you're gonna behave as a developer or something like that, all right? Okay, so here's an example of a very simple prompt. This is just expecting some completion, all right? So if you give this prompt here, the input prompt to the model, the sky is, the model will very likely complete with the word blue, just because it saw this so many times during the training, okay? So that's a very simple example of a prompt. And here we have a prompt with an instruction, okay? So if you look there, so the prompt is classify the sentiment of the following sentence. The meal was awesome, okay? And the model could output this result, sentiment positive. Okay, so here you're instructing the model to perform the sentiment classification. And here's an example of a prompt with a constraint. Recall that I said that sometimes you want the output to be constrained to something. And here we have an example. So classify the following sentence into neutral, negative, or positive. So the meal was awesome, and the result could be just positive. Again, if you are parsing this output, and if you look back on the previous slide, you don't want the sentiment to be here because this will make your parser to fail. That's a very easy and lightweight way to enforce some output results. And here I have an example of a more complex prompt. Okay, so on the left-hand side, you see in context learning. So you have there, an instruction, answer the following mathematical reasoning questions, and then you have, few short examples. Okay, so you have a question. If you have 12 candies and you give 4 candies to your friend, how many candies do you have left? And then you have the answer. The answer is 8. And you have another example. And then you leave the model with this question. Sam has 12 marbles. He gives 1/4 of them to his sister. How many marbles does Sam have left? And the LLM will very likely produce an answer that follows these examples that you gave previously, okay? So these are called the few shot examples. You probably heard that before. And we have an example of a chain of thought prompting. This is a prompting technique that allows, makes the model reason step by step before it arrives to an answer. Okay, I'll be talking more about a chain of thought later here. So this is prompt, okay? This is the way you instruct the model to do something, and you have many different techniques to achieve good performance when you are instructing the model. And I will be talking about these techniques now. So the most basic one is zero shot, where you directly instruct the model to perform some task, okay? So there is no examples, it's very likely something similar to what I showed, the sky is blue, okay? But you have instruction, you're asking the model to perform some task. You have what we call few shot examples that will give examples to nudge the model to produce some answer. Okay, we have chain of thought that will enable the model to perform this complex reasoning, okay, and think step by step. And then after chain of thought, these other two, self-consistency and three of thoughts, are actually built upon the chain of thought, and it's an augmentation of this technique. Okay, so self-consistency, actually, you have multiple chain of thoughts path. Okay, it tries to it's inspired on how we actually solve problems. We usually don't arrive at an answer directly from a reasoning path, but we try many different ones until we arrive at the correct answer. And tree of thoughts, it's again an augmentation of chain of thought, where you actually produce a lot of those reasoning paths, and you can backtrack and evaluate them as you explore or search over this tree. Okay, so these are, I would not talk about zero-shot prompting. It's just, directly instructing the model, but I will talk about these other 4 prompt engineering techniques with a little bit more care now. Okay, so few-shot prompting, as I showed before, you're gonna basically show some examples on how you want the model to generate the output. Okay, so it's based on this principle of meta-learning, where you teach the model from the prompt by itself. Okay. So here's an example, nothing better than an example. So, these are the few-shot examples. Okay, over here. So circulation revenue has increased by 5%. Again, this is a sentiment classification task. Okay, that we are trying to achieve here with this prompt. So you have positive for this, you have a neutral for this sentence here, and we have negative for this last sentence here. And then I provide the model with this deacquisition. We have an immediate positive impact, and you expect the model to generate positive as a result, okay, as a generation from whatever left here. So the examples are priors to the model, okay, and the model is trying to follow what saw previously. And there are papers showing that few-shot examples, few-shot prompting actually improve accuracy in some benchmarks. So this figure here, this strong line, okay, it's actually aggregate performance across multiple benchmarks, okay? So the lighter lines are actually the performance on the individual benchmarks, and the strong lines are the aggregation of these lighter lines, okay? And here we're just increasing the model size, the parameters, the number of parameters of the model. And this was a classification task benchmark, so you have accuracy here. And as you can see, well, we can see 2 things. The performance improves as you improve the model size, but also you can see that, zero-shot performs worse than few-shot. So you give some examples, and the accuracy increase, okay? And also you can see that few-shot, it's slightly better than just giving one example. So one shot here means I give just one example on the few-shot component of my prompt, okay? And there is a very interesting result because these labels are hard to get. Usually need annotators that cost, but there is a result that is, I'm just trying to bring here that is quite interesting, that asks, do correct examples matter? Like, do these labels that you give together with the few-shot prompt, do they need to be correct in the sense that humans understand, okay? And the result shows that, this input label mapping has very little impact on the performance of the model. Okay, so typically the labels don't need to be exactly correct, but they need to follow some properties that I'm showing here. Okay, this is just the result of that same paper. Okay, so what we're seeing here, we have gold labels. Okay, and gold labels are represented by this yellow line here, and gold labels are the correct labels. Okay, and we have random labels, which is represented by the blue lines here. Okay, random labels is I get an input, and I just label that input with a random label instead of the correct label, instead of the gold label. Okay, as you can see here, we have also accuracy, and K is the number of few-shot examples. And as you can see, like if you get a random label or if you get a gold label, the difference is not that big, okay? Both for a mode choice here, a task, okay, and a classification task. Both you can see there's not a big difference, especially when you give more labels, okay? But we have to be careful with these follow concerns here. Okay, first is this distribution of the input task. Okay, text. Sorry, just one thing here. So when we say X, we are saying, every few-shot example has 2 parts. So if you look back here, okay, Circulation revenue has increased by 5%. That's it. That's what we call X on those slides. And the label positive on the first example there, it's Y. Okay? So getting back to those slides, just to explain what's X and Y here. Okay? So when you're talking about the distribution of the input tax, the underlying distribution of the axis, okay, they need to be on the training data. That's the result. So if you want to see a performance improvement when you're using few shot examples, you need to make sure that the tokens that you see there were on the training data. Otherwise, the thing won't work. Okay? And we also have the label space. So the underlying distribution of the labels, they need to be conditioned to a label space C, so you can see performance gains. So these labels also need to be on the training data, okay? And one important thing is also the format of these input label pairs. I will show more results on this, but if you change the format, for example, if you change, instead of adding the semicolon, you just add a line break, that can change completely the performance of the model, okay? So the way you format the input label pairs will make a lot of difference. I know this is counterintuitive, but it makes a lot of difference, and I will show results that prove this point, okay? And a few shot examples are great, especially when you're doing classification, but they have very limited reasoning capabilities, okay? And we have prompting techniques that solve this issue, okay? So we're seeing here a few shot example, okay? And it says, Roger has, just to illustrate what I'm trying to say, okay? The question is, Roger has 5 tennis balls, and he buys 2 more cans of tennis balls. Each can has 3 tennis balls. How many tennis balls does he have now? So it's a question answering a type of problem, okay? And then in the few shot example, we're saying the answer is 11, okay? And it's correct. And now comes the question, okay? The cafeteria had 23 apples. If they used 20 to make lunch and bought 6 more, how many apples do they have? And the answer produced this, the model produced this answer. The answer is 27, okay? See that it tries to follow the example, just arrive at the answer directly, okay? And the answer is incorrect, okay? So using these few shot examples or few shot prompting will not make you arrive at correct answers for some problems, especially question answering, math problems, and so on. So what people do is they use this chain of thought prompting, okay, that helps the model to break down a complex task into smaller subtasks, solve each of these smaller subtasks until it arrives at a correct answer, okay? So what chain of thought prompting is, it's a series of intermediate natural language reasoning steps that lead to this final output, okay? And every prompt in a chain of thought prompting will consist of a triple, which has the input, the chain of thought, and the output, okay? And here is an example. Again, I think it's easier to understand things with an example. So it's the same problem as I previously showed, okay? So Rogers had 5 tennis balls and etc. Now, what changes is, instead of me giving the model the answer directly, I show the model how it should break this problem to arrive at an answer, okay? Or how to reason over the problem. So Roger started with 5 balls. 2 cans of 3 tennis balls, each is 6 tennis balls, okay? 5 plus 6 equals 11, so the answer is 11. Now there you are showing an example of how the model should reason, all right? And I left to the model the same question, all right, about the cafeteria and the apples. And now the model, instead of arriving at the answer directly, okay, the incorrect answer, it's actually, trying to reason over. So the cafeteria had 23 apples originally. They used 20 to make lunch. So they had 23 minus 20. They bought 6 more. Now they have 3 plus 6 equals 9. And the model could arrive at the right answer here, okay? So we're seeing an example of an input, a chain of thought, okay, here, and an output. So there are multiple of these components, all right, in this prompt particularly. And the chain of thought component, okay, on the triple, it's actually here, all right. So that's pretty much what you do to enable the model or to nudge the model to reason before arriving at an answer. Okay? This is very useful for question answering, math problems, and things that you need to break a complex task into smaller ones. Okay? And what people realized later, there is something called zero-shot chain of thought. So instead of giving an example of how to reason, you don't even need the example. You just ask the model, let's think step by step. Okay? There's a paper that shows that actually there's a lot of different ways of asking the model to reason to think step by step, okay? But the original paper that kind of proposed zero-shot chain of thought was using let's think step by step, okay? So you see here in this prompt that you just have the question, okay? And there is no example, okay? You just finish the prompt saying let's think step by step and ask for completion, okay? Ask for the model to complete the prompt, okay? And the result is, surprisingly, that the model follows this instruction. It really tries to break down the question and to reason until it arrives at an answer, okay? So this is called, again, zero shot because we don't have any examples. We just ask the model to think step by step. And there are many different ways to ask the model to think step by step. This will work in some models, but not very well in others, so we need to ask the right way. Okay, so chain of thought was a very seminal work, okay, over this idea of actually asking the model to reason. And then there was another, a second technique that was built on top of a chain of thought that's called self-consistency. And the idea here is to allow multiple reasoning paths. That's the core idea of self-consistency, okay? And it followed three steps, okay? So you first prompt the foundational model, use chain of thought prompting, pretty much as we shown previously here, okay? Then you're gonna replace the greedy decode. So instead of just getting one response, one chain of thought, okay, from the model output, you're gonna get multiple. And I will show you later how you're gonna get multiple, but for now, just imagine that there is a way to get multiple outputs from one prompt, okay? So the model will produce, I will have this chain of thought, okay, this path of thought, and I will have another one, and I have a third one and a fourth one, or how many you wanna sample, okay? And what you're gonna do at the end, on the third step, is gonna average out these reasoning paths, okay? So remember on the question answering, the question was a math question. Okay, so you arrive at an answer, at a number, all right? Saying, the result is 9, the result is 11, the result's 9 again, depending on the reasoning path that you were actually sampling, okay? And at the end, you just average out. You could use, for example, majority vote, okay? So if the majority of the reasoning paths arrive at 9 as an answer, I will get 9 as my final answer, okay? So here again is an example. So chain of thought, it's here. We just saw, like you do the prompt, you pass to the language model, and you get the first reasoning path that arrives at a certain answer, and you assume that's the correct answer. All right? That's chain of thought. So self-consistency changed this a little bit. So instead of get one single answer, a reasoning path, all right? You get multiple from the language model. So here's the prompt, all right? It's a chain of thought prompt. So you're gonna pass through the language model and you're gonna get multiple reasoning paths. So the first one here, it says, the answer was 18. For this one, the answer was 26, okay? For this one, the answer was 18 again. So if you use, for example, majority vote, that's a way of marginalizing things, you're gonna say the final answer is actually 18, all right? So that's the core idea of self-consistency, having multiple reasoning paths and averaging them out until you arrive at the answer. But use chain of thought prompting as well. The only difference is to get multiple reasoning paths, okay? So here's an example. Here is just chain of thought examples, okay? Pretty much as we saw before. And I have a question. When I was 6, my sister was half my age. Now I'm 70, how old is my sister, okay? And now you have multiple results, all right? You have this result that arrives at 6, 7, this one 6, 7, 2, this one arrives at 35. So what you do at the end, you get all these answers, process them, of course. You're gonna parse and etc. And then you're gonna say, okay, if you use majority vote, for example, you'll get 6, 7 as my final answer. Okay? On top of this, they built something called tree of thought, which is another technique that also have this idea of using multiple reasoning paths, but now you have a tree of reasoning paths and you kind of search over this tree, doing evaluations of the reasoning paths, okay, and the results with the own foundation model, okay? So this technique has 4 steps. So first, you decompose the intermediate process into thought steps, okay? This is exactly what a chain of thought also does. You generate potential thoughts from each state, okay? You heuristically evaluate these states. You literally ask the foundation model to evaluate what it just produced, okay? If it's a question answer, as we showed before, and it's math involved, okay? So you produce the first step of the chain of thought, and then you ask the LLM, like, is this promising? Is this going in the right direction? Does that look, consistent somehow? And then you apply a search algorithm at the end to kind of backtrack and also keep evaluating more states, okay? So, as I mentioned, the first step is to decompose the tree of thought prompting, okay? And here you're gonna have to look at your problem to really understand how we're gonna decompose the tree of thoughts into thoughts, okay? Into thought steps. So for example, if you have a crosswords problem, probably your thought will be a couple of words, okay? If you're doing math solving, your thought could be a line of an equation, okay? If you're doing creative writing, your thought could be a whole paragraph of the writing plan, okay? And as a guideline, like the thought should be small enough so the foundation model can generate it, okay? Promising results, and should not be big enough that you cannot evaluate the thought, okay? And then you need to generate these thoughts. So you can basically have 2 ways. You can sample through from a set of chain of thought prompts, okay? That's how you generate a new thought. Or you can also use what they call propose prompt, okay? Which is basically, you give some chain of thought examples. Sorry, just to give some context here. This prompt is for the game of 24. So you were asking the model to solve the game of 24 problem. And this game of 24 is very simple. You give 4 integers, and you need to decide if there is a way of performing operations, minus, plus, and etc. over these 4 integers, such that you arrive at 24 as a result. Okay, that's the game of 24. And here it's a prompt asking the model to solve the game of 24. Okay, so you have chain of thought examples here, and then you have an input, which is 4 integers. Okay, and that's the proposed prompt. You ask for possible next steps, and then you're going to have a lot of different possible solutions, and you can also sample from these solutions as a way to generate tree of thoughts. Okay. And then you need to evaluate each of the generated thoughts, okay? And you can use, some heuristics to determine if you should keep exploring more states. So if you should generate another thought after the thought that you just generated, okay? And you have 2 strategies to reason over these states, okay? So you can have a value prompt that will generate a value, okay, a number for you to kind of say what's the value of, or what's the how good this thought that I just generated is, okay? Or you can have a vote prompt, okay, which is a prompt that asks to look at a set of thoughts and select the best one, okay? So here is a value prompt, an example of a value prompt, okay? It says, evaluate if given numbers can reach 24 with sure, likely, or impossible. These are the three outcomes that can come, all right, that the model can produce. And then for this one, it says sure, because you can definitely arrive at 24 by summing the two numbers, okay? And then you have more examples like this one, and then you give the three numbers here, okay? Or you can have what we just call the vote prompt. So you have lots of different thoughts, okay? And then you have this prompt here that basically asks to evaluate which one is the most promising one, okay? And then you're gonna use that one as a thought to the tree of thought prompting, okay? And as I said, there is a search algorithm at the end, so you can basically use, breadth first, which will maintain a set of, the most promising steps or thoughts in the tree. And you can have that first that will, evaluate a full chain of thought before it backtrack and try another one, okay? So here is just an example of how this is implemented. So let me start with the right-hand sided figure. I just want to illustrate here what this is. So each node here, it's a thought, okay, a decomposed thought. And sometimes you just, you say, during the evaluation, you say, okay, this thought here is not very promising. So we'll backtrack and then explore another one, okay? Oh, this one here looks promising, I will keep exploring. And then you arrive at this one and say, okay, this is not promising. This is not promising happens during the evaluation of the thought, okay? Until you end up getting a path here that, every step, every thought, it's actually promising, and you arrive at a certain answer, okay? This is how this backtracking mechanism exists inside the tree of thought, okay? And here's an architecture implementation, an architecture to implement a tree of thought, and use this prompt agent module, okay, that instructs the LLM to generate an intermediate solution. You also have this checker module which checks the validity of the generated intermediate solution. This is the module that does the evaluation, okay? When the evaluation says, okay, this is a promising thought, let's keep exploring it, okay? You put this thought on the memory module, okay? Now here, the difference between the breadth and that first is if you're using, removing from the memory module as a queue or as a stack, right? And then you have the tree of thought controller saying, signaling the prompt agent if it should keep exploring that path or not, okay? So this is the tree of thought. And here, finally, just to wrap this up, the difference between chain of thought, input, directly out inputting, and self-consistency, and the tree of thought, it's illustrated here, okay? So direct input, output, the leftmost side, the left-hand figure, you're just, instructing the model to reply to you for a certain question, okay? Chain of thought, you break down, but you have just one path, okay, one reasoning path. Self-consistency, we have multiple paths, but you do not do backtracking or anything. You just explore all of them, and then you do some type of, averaging them out. And tree of thought, you have this search algorithm on top where you can do backtracking, and you have also this evaluation when you ask the foundational model to evaluate its own produced thought, okay? Just to wrap this up. And that's it for prompting engineering techniques. I just want to give this flavor. There is much more, but just for you to have this very basic understanding of the core ideas behind these prompt engineering techniques, okay? And I will talk now about sampling and decoding. So the idea here is that, these autoregressive models, what they do is like they generate token after token. That's all they do, okay? So you give these prompts as a prior to the model, and then what we're gonna do, the model gonna do is like calculate a probability distribution for each of the tokens that it knows, okay? It assigns a probability, and then you need a piece of software that we call decoder, okay, to select one of these tokens. A very agreed decoder will always select the token with the highest probability, okay? But we know that doesn't necessarily, the grid decoder doesn't necessarily lead you to the final response being the most likely one. Okay, so you have many different ways of decoding the output of the foundation model. But the point here is, at each iteration, it outputs a probability distribution, which is the probability of all the tokens, okay, or the individual probabilities of the tokens, okay, with the prompt and what it has previously generated as the priors, okay? And decoding would then use the search algorithm to find an approximate sequence that leads to the sum of the outputs being, the highest one. You have, as I mentioned, many different ways of sampling for the decoding. So you can do random sampling. You just select the next token according to all predicted probabilities. So it's like the roulette method, right? You just, the most likely one to get is the token with the largest probability, but you can always have a possibility of generating or of selecting the other tokens as well, okay? It's like, spinning a roulette, okay? So you can also do top K sampling, where you select the token from one of the K tokens with the highest probability. So you have, all the tokens, you select K is an integer, okay? Let's say 10. Then you're gonna cut and select one of the 10 most likely tokens, all right? And you can also do top P sampling, okay? Which is, P is a threshold that you set between 0 and 1, so the probability threshold. And then you're gonna only select tokens that are above this threshold. So if the threshold is, let's say, 0.5, you're gonna cut on the 0.5 probability token, and anything below you will not select, or you can select anything that it's above, okay? And you have, many, basically two search algorithms for decoding here. There are others, but I will show these two. So grid, select the token with the highest probability at each generation step T. So you know exactly where always getting the token from the top probability. But you can also use beam search that will explore the space of possible generated sequence much more than greedy search, okay? And how beam search works is like, first of all, it keeps a fixed number of K possible sequence of length T at each iteration. So there is a parameter on beam search, which is K, which is the number of sequence that we're keeping on memory at each step, okay? So let me illustrate to you what a beam search looks like. So BOS here, it's the beginning of sequence. It's a special token that you're just signaling, saying, okay, I'm starting the generation of a sequence, okay? And now, for this example, by the way, K is 2. So you are keeping 2 paths at each iteration, all right? So after the beginning of sequence, you need to generate tokens, okay? And you are using a decoder. So you are selecting tokens somehow, okay? For example, you're getting the two most likely, okay? So these tokens will be he and I in our example here. So this is the first iteration of the beam search, okay? Now you're gonna unfold. You're gonna do another iteration, all right? So from he, all right, I will generate 2 other tokens, and I will select 2 other tokens from this sequence in here, hit and struck, all right? And on top of here, we have the probabilities of each of the generated tokens, okay? So this one, it's minus 1.7, for this one, minus 2.9. And I'll look at the other path as well here, okay? From I will generate was and out. And here are the probabilities as well. Now, the beam search algorithm will eliminate, okay, the less likely token such that you still keep only 2 paths, because K is 2, okay, in memory. So you eliminate this struct token and this out token, and now we have 2 partial sequence generated, okay? He hit and I was. And I will do this again on the next iteration, okay? So from this path here, we have he, hit, A, and me, all right? And from this here, I was hit and struck. And again, I will look at the probabilities and I will eliminate the 2 here, and such that I only keep K, also 2 paths at the same time. And I will do this until I finish my, my completion. And the completion finishes when I produce a end of sequence token here, okay? So the generated, in this example, what we end up generating was, hit me with a dart and pi, okay? Because everything else was just eliminated. And then, of course, at the end, the beam search will get the sequence with the largest total probability. Okay, so the sums of probability is the largest, because you're going to end up with 2 at the end, right? Okay. So if you ever happen to interact with foundation models through an API, you probably saw these parameters here, and these are the decoder parameters. Okay, so temperature, and the P parameter. So temperature will control the weight that you give to the tokens other than the most likely one. Okay, so it will kind of determine the level of determinism in the generated sequence. Okay, and top P, remember that we had, I just spoke about, top P sampling. So you select only the tokens that are, above the P on the sequence of tokens, ordered by the probability. Okay, so P here says exactly P. So, how many tokens you can get at each sampling step. Okay, and a good practice, to change these parameters when you're setting hyperparameters from your API there. Okay, so this is pretty much the basics on prompting and what we need to also set up in terms of parameters for the decoder. Now we'll talk about something called the fragility of prompts. Okay, prompts are very fragile in the sense that when you change them, even very small changes in the prompt will cause your foundation model to produce quite different response. Okay, and this have strong implications for software engineering that I will also discuss in a minute. But I just want to illustrate what prompt fragility is before I move to these software engineering implications, okay? So first of all, the implications about portability, okay? So you cannot write a prompt to one model and magically move this prompt and make it happen or make it perform well in another model, okay? So, you need to tune your prompt every time you change a model or every time you experiment with a new model, okay? So there is this interplay. You never know if the problem is with the prompt or the model by itself as well, okay? So here it's a result that's showing, a GPT-4 and how it behaves for a certain task in March 23 for the same task, same prompt, same everything, okay? And in June 23, excuse me, you can see a very different performance on these 2 versions of the model, okay? So the model released in June simply is much better than March. And the point is it behaves differently for the same prompt, okay? And the same here is shown for, GPT-4 and GPT 3.5, 2 versions that were, probably released on these dates, but this is not the release date, this is just when the experiment ran, but we believe they are different models, okay? They also have very different performance with the same prompt to the same data, okay? So that's the point with fragility, okay? The foundations model will show a performance variability based on the performating, the ordering, and the choice of the training examples in prompt. This idea of fragility, it's explored in the literature more regarding few shot examples. So there is a lot to be done in terms of understanding how fragility really works. So I think the papers that I could review basically try to change the format of the few shot examples in terms of the order of the few shot examples or how the few shot examples are written in terms of the separators and so on. I will show a little bit more on that, but just to mention that there is a lot to be understood in terms of how fragility really affects, or how prompts are really affected by these variations in the prompt. Okay. So the first result shows that foundations models are very sensitive to subtle formatting changes. Okay. So for example, if you switch a column, okay, to a dash when you're using a few short examples, or if you're using uppercase and lowercase for instructions, this will change. Even if you don't change the word or the examples by itself, okay, you just change those tokens, that will produce, make the model produce very different results, okay? The order of the few short examples also affects model accuracy, okay? So certain permutations, so the order that you give the examples will be better than others. You know, for example, a positive example placed last in a sentiment analysis prompt might lead to bias toward these positive classifications, okay? There is also papers showing this. And the other results that, you know, sensitivity to formatting is not consistent across different models or tasks. So some models are more sensitive, you know, and some tasks also lead to more fragility than others. So just to illustrate this, you know, this is a prompt, okay, with few short examples, okay, and the examples are this, you know, passage, and we have some text here, and we have answer and some text here, okay, and this was the original formatting. So we're gonna these other boxes are just variations of this original formatting and how they're affecting performance on a task that was evaluated with accuracy. Okay, so the original prompt brings me here in terms of performance. Okay, and then instead of having this, I do not break the line between the passage and the answer. I actually, you know, the spacing between fields is different now. It's just a space. There is no line break. And that brings me to this accuracy here, okay? So now the modified separator and spacing. So I do not put the semicolon there, okay? And I just give the examples this way, and I have this accuracy, okay? And this poor guy here, the only difference is the space, okay? I just removed the space, and the accuracy brought me here. From something close to 0.8, okay, or 0.7 to 0.036. So, you know, there is a huge search space to explore, and do you want to pay people to just, you know, oh, maybe I will try with space, without space? We don't know. We're gonna get there, okay? So what are the factors that influence sensitivity? So first of all, there is a majority label bias, okay? So that leads the model to predict training when you're using a few short examples that appear more frequently in the prompt. So first thing, we need to balance those examples, right? If we want to somehow mitigate the sensitivity, okay, of the prompt. There is also something called recency bias. So these foundation models, they tend to give more weight to the information that is presented closer to the end of the prompt. That's where the foundation model will put more attention, okay? So if you put these few short examples at the end, there is a bias of the model kind of classifying things with those labels that are at the end, okay? And there is also something called common token bias that leads the model to prefer answers that are more frequent in its pre-training data, okay? So, you know, as the way you also train or retrain the model also will influence this prompt fragility, okay? And why does that matter? So first of all, these fluctuations will raise questions about the model's ability to generalize on a certain task, okay? You never know if you just found by chance the good prompt that actually performs, or if it's just the model that it's really good at a certain task, okay? You know, and then when you're doing research, basically, oh, I tried this prompt here and I got an amazing result, okay? Or I got a poor result. So how many prompts are we really trying to perform a certain task, right? So when you're doing research, this is very complicated. Okay. There is a matter of also reliability, right? When you're building systems, so these unstable outputs will make the foundation models less reliable on these real-world applications. Where if the prompt is coming from the user, you never know how the user will write the prompt. So maybe when you're trying things during development time, things are amazing, working very well, and then on the real world, you will not see that same performance just because this small variability in the prompts. Okay, and in terms of user experience, that will definitely reduce trust on your final system. Okay, we also have 2 papers that try to quantify those prompt fragility. So they give us some metrics to evaluate how a model behaves in terms of fragility of the prompts. Okay, and the first is called performance spread. Okay, it's very simple. So you have a task, and you evaluate this task. You have some metric to evaluate the performance of that task, and you get the maximum performance minus the minimum performance over multiple trials. Okay, and then that's what we call performance spread. But over multiple tries or over multiple variations of a prompt. Okay, and if the spread is too large, of course, that means that model it's very sensitive or it's very fragile in terms of the prompt variations. Okay, we also have something called sensitivity that measures a change of predictions across rephrasings of the prompt. The nice thing about this metric is that it does not require access to ground truth labels, because you simply don't need them. Okay, because you're going to rephrase the prompt and you're going to verify how it changes. So you don't really need these ground truth labels. Okay, and it's a guide to compare the robustness of different LLMs to variations of the prompt. Okay, so the result is like highly sensitive foundation models may require significant prompt optimization efforts. So if you see that your foundation model is too sensible, you might want to invest more into find good prompts. Okay, and the final metric is called consistency, that measures how predictions vary across rephrasing of elements of a prompt to the same class of a certain classification task. Okay, so being consistent suggests that the prompt rephrasings cause similar mistakes across all samples of a certain class. Okay, and an inconsistent LLM behaves unpredictably among samples of the same class. Okay, so that might indicate that the problem is not in the prompt, but on the model itself. So we invest more into maybe fine-tuning the model or modifying the model somehow, but not much effort into finding the best prompt configuration. Okay, and again, these papers show some interesting results. So just to show what's showing here. So this is the performance spread. Remember, performance spread, you run variations of the prompt for the same task, okay, and you get the better minus the worst performance. This is performance spread across prompt formats, okay? And what we're varying here on these box plots are, these two are the same model, same size, same model, okay? But I'm varying the number of few shot examples that I give to the model, okay? And as you can see, there is some variation among, giving more or less few shot examples, okay? So each pair of box plots here, it's varying only the number of few shot examples, okay? But now we can also see like this is different models, especially when you go from Llama to Falcon, you can see a very, very different distribution of performance spread, okay, across these prompt formats. And here we are also showing, so here like each data point here, it's multiple runs for the same task, okay, but multiple variations of a prompt. And as you can see, like, these are the same models, but they have different sizes, okay? So here we have Llama 2 7B, here Llama 2 13B. And as you can see, like, there is also variations between the size of the models, okay, in terms of performance spread. Here, I'm just also showing, you know, the significant performance spread regardless of instruction tuning, because this is Falcon 7B with instruction tuning, and this is without, okay? There is even more variation. And finally, the number of few shot examples. It's also not, you know, the same when you vary the number of few shot examples. And finally, I'm showing here, you know, that increasing the model size, it's beneficial in terms of the variation that you see in terms of performance when you change the. Here I'm varying only the order of the few shot examples, okay? In all these figures here. So we have 4 few shot examples, so we have 24 possible orders. And I'm varying this here, and I'm showing also that, you know, increasing the number of few shot examples does not make these variations lower. You know, adding training samples also doesn't make this much better. And the performant prompts are not transferable across models. So you're gonna see that your prompt is working very well in a certain model, and then we'll try to, you know, to transfer or to port to another model. The performance might increase or might decrease, very likely decrease. There is another issue with prompting that we call context window sensitivity, okay? So what's context window? It refers to the maximum number of tokens that you can input at the same time to a foundation model, okay? So every foundation model has a context window limitation, so it's the maximum amount, okay? And the size of your prompt, okay, so how many tokens you have in your prompt will also affect the result that you're gonna see from your foundation model, okay? So what can happen if you, for example, exceed the maximum number of tokens that a foundation model can handle? Okay, so you're gonna see truncation of inputs, okay? So if the context window is exceeded, the model will truncate the text from the beginning or the end of the prompt, okay? So you can, for example, lose critical context that you gave to the model, okay? And you can, as a result, get wrong answers, as the model can, you know, just miss this information that you thought would be given to the model, but it's actually not, okay? You can also see what we call contextual degradation. This is proof, okay, that longer prompts will make the model perform worse for the same task, okay? So you always have, when you're writing prompts, you need to balance between, you know, be comprehensive and be short on your prompts, just because, you know, results demonstrate that these longer prompts, they don't work very well, okay? And also, the longer the prompt, the more, the coster is your inference, okay? So the inference gets slower because you are processing all these tokens on the input, okay? And they get more resource intensive, okay? So you're probably gonna spend more energy, and you're gonna, you know, occupy your computing infrastructure, which might translate as practical constraints in real world applications, okay? So longer prompts are usually problematic, and we call this, you know, context window sensitivity. And there are ways to kind of mitigate this. One, it's doing what we call condensed summaries. So here you ask the LLM to summarize the response. So for example, you have a dialogue, okay, application. So you ask the LLM to summarize the results with the prompt, and then you concatenate all together, and you pass along again to the foundation model. So this is a way to kind of compress, okay, the prompts, so they get smaller. We just mentioned that longer prompts are problematic, so they get smaller and likely better, okay? We can also do what we call prompt decomposition. So you break the prompt into smaller, consistent segments, and then you pass one prompt after the other, one segment after the other, okay? But you know, you need to maintain coherence, and this is not always very easy, especially for, you know, tasks that require these long-range dependencies, okay? So for example, if the LLM is tasked for writing a chapter of a book, for example, you really need the context of the beginning of the chapter, okay? So this prompt decomposition might not work in this situation. And you can always use memory augmentation. You know, you just record in an external memory parts of the prompt, and you pull in back when it's necessary, okay? These are ways of mitigating these context window sensitivity. And in RAG systems, I don't know if someone mentioned RAG yesterday, but okay. I don't know if someone mentioned RAG yesterday, but RAG is basically the combination of, you know, prompting foundation models with information retrieval. So you get the original prompt, you first retrieve information from a information retrieval system, and you put back on the prompt as a context, okay? And during this RAG process of, you know, retrieving from an information retrieval system and putting back in the prompt just gets longer, right? It's very common to get really long, especially when you have too many documents being retrieved, okay? So the idea here is the following. So you retrieve multiple documents, and you just get the first document and you append to the prompt, and you pass along to the foundation model, okay? You're gonna get a token distribution from there, all right? Step by step. And you then get the second document, you append to the prompt, and do the same. Just pass along to the foundation model to produce its token distribution, all right? And you get the third one, and you do this for all the documents that you want, okay? For the top K documents. And now you just average out the token distribution, okay, as a way to sample the tokens as the final output, okay? So again, this has a drawback, which is you're doing multiple foundation model calls, all right? So that might be costly. However, you are, at the same time, kind of mitigating the problem with the prompt being too long because you're just inputting too many documents at the same time on the prompt, okay? So that's a way to kind of try to solve this problem, okay? Now, in terms of engineering of foundation models and to maintain, to evolve these systems, prompt sensitivity has very strong implications, okay? So first of all, there is prompt drift. So as these foundation models will evolve, will be retrained, will be trained with new data and so on, they will evolve, okay? New versions or new release of the model will come up, and then the prompt that you had previously that you spent a lot of time kind of tuning, changing format, changing order of the examples and etc., it just doesn't work anymore, or works worse, okay? So there is a regression as you change the models, okay? And also the implication is also that you need to test for these regressions, okay? So you need to have these regression tests in place such that you can, you know, with confidence evolve these models and know when these regressions were introduced. Okay, so let's talk a little bit more on these aspect of evolution and management. So right now what's happening, most of the case, is that prompts are being manually tuned, okay? All these variations are explored by a human, right? And I spoke about format variation, but you also have, you know, wording variations. You use synonyms, you know, and so on. So the space to be explored, it's huge, and it's being explored by someone, okay? How? Very iteratively. Usually we are doing experimentations. I try with a variation, got better, I will use this one. And then you change something else, got worse. So, you know, it's very iterative, it's very experimental. All right? You are always trying new variations of the prompt, attempting, checking the performance, and getting back there. It's very human-centric, okay? It's being done by someone, by a human in the loop, all right? And again, we argue here that the search space is very, very large, okay? And you are always try to, you know, balance specificity and generalizability, okay? So overlay specific prompts might limit flexibility, okay? So when you see new case on the real world, the prompt won't make the foundation model perform very well. But very general prompts, might also reduce performance just because you can't, overreach all the cases. All right. So right now the software engineering process is driven by humans, exploring this huge space of possible prompt formats and variations. Okay. And how this is done? Again, you start by defining your objective. You design some initial prompts. You test them in a very controlled setting where you have, data for or a benchmark or something, okay, for you to evaluate your prompt. Then you iterate and try to modify the prompt somehow. And finally, you arrive at a prompt that you believe it's good enough. You're gonna deploy. You're gonna keep, monitoring the performance of this prompt after deployment. And you're gonna do adaptations as you see that there is some drifting happening or the prompt's not behaving as it should or as it behaved during development on field. Okay? And then you need to maintain and update these prompts. So this life cycle is also carried out right now, typically by humans. Okay? And when you see a problem, you need to debug the prompt. Okay? And it is usually very complicated because you need to know what I'm changing the prompt, okay, and how this is causing my foundation model to behave differently, okay? What should I change? The order of the few shot examples or the space there that it's actually the problem? You remember the figure that I just removed one space and I went from 0.7 accuracy to 0.03 accuracy, okay? So the point here is that developer needs tools, okay, that allow them to pinpoint the areas of the prompt that requires adjustment. And we are just writing prompts, on your IDE, you usually don't have this support. Okay? So this debugging is basically this process of analyzing, refining the prompts to identify, understand, and fix the issues that are affecting the performance or the reliability of the foundation models on a certain task. Okay? And right now, this is very HCI thing, but again, I'm just showing here how people are actually helping developers to debug prompts, and they use these explainability techniques. So what we are seeing here, okay, it's a prompt editor. It's like a prompt playground, okay, and it's helping you to understand or helping the developer to understand which part of the prompts are more associated with a certain output, okay? So here you have basically, a prompt editor where you're gonna write the prompt. And then, you're gonna have multiple sequences that are generated and you can select them here, okay? And then you're gonna have these colored sentence where stronger colors mean this is more or this is contributing more to the output than these lighter colors here, okay? So you know that this part of the prompt is being kept more attention and that very likely you should pay more attention here as well when you're changing things, okay? So changing this part of the prompt will certainly cause bigger changes in the output, okay? Much more than this one, for example, okay? And you can also, select some segments to explain here. So this is a work done by Google using these explainability techniques to help developers to debug prompts, okay? By showing where the prompt you should put more attention or should change more and which part of the prompt will cause more or bigger modifications on the output, okay? And this prompt playground here also have, side-by-side difference in prompt, so you can see, what you changed and how it affected the output. So that's one of the works that are trying to improve the developer experience on debugging prompts. Okay. And when you're prompting, you need to systematically evaluate the outputs, and you usually do that, by testing some properties of your output. Okay. So if it contains certain word that you might want or you might not want, okay? If it matches some properties there, or maybe even if it's equals to something that you expect, okay? So this is assertion, pretty much as we know from traditional testing, okay? Foundations model can also be used to assert more complex properties. You can have an evaluator foundation model to check if the response has some property that it's not very easy verifiable by a fixed logic, okay? And you can also use these assertions with foundation model to produce a task failure score that when it's below a certain threshold, you just say, okay, this task here just failed. I need to do something on my prompt, okay, to fix this issue. And again, these prompts, they need to go under a lot of management. So just bringing here an example of what LangChain Hub is doing right now, and just to illustrate the concerns that we have to have about these prompts, okay? So first of all, sharing, okay? Especially in a corporation environment, when you write a prompt, maybe you want to share with someone and you want someone to contribute to your prompt as well. So prompt is being here treated as any source code, okay, where you can collaboratively edit the prompt. And also you need to version the prompt, okay? So you have here, this is probably managed with Git. So you have, versions, SHAs, you have also, branches and everything, and you have versions. So prompts will have to go over all these type of management that we know about source code. We also have to apply to prompts, okay? So the question is, what else we have, okay, that we don't have or we don't need for traditional source code, okay? That is just a teasing and just for us to think about it. And finally, so I try to show here that, having someone, having a human developer kind of trying to find these prompt variations and which one works better in this huge search space might be not the best approach. So let me show you where things are heading to. And we believe that actually will be the future. And this is prompt compiler, okay? This is not new, so like the state of the art, state of AI report in 2023, we're already pointing out to this direction of, prompt compilers being something. So instead of manually searching over this search space, we actually would have an automated process doing this, okay? And here are how these prompt compilers generally work, okay? So let's start from here, okay? So we have basically two steps. One is the inference step, and then we have an optimization step, and I will try to explain what happens here, okay? So we have input data. This can be like instance of the problem that you were trying to solve with your foundation model. This can be like instance of a benchmark, for example, okay? And then you have the things that you want to optimize in your foundation model program, okay? Foundation model FMware program. Okay, you have parameters of the FMware components. Could be, for example, the hyperparameters of your RAG, okay? Could be, the hyperparameters of your agents architecture, like the number of agents, how the agents organize themselves, if you have a memory component or not. Any parameter that can be optimized and that you want to check how a new prompt will actually affect it will be here, okay? And you have the prompt templates that you write in your program, okay? The prompts that you just saw here. And these are everything that can be optimized by the compiler are here, okay? Optimized by the compiler, why I said that? Because this compiler is search-based, okay? You will try to find the best configuration that leads to the best result of the whole program, okay? All right, so from here you get your prompts because the input data fills up the prompt templates, so you get, prompt instances that are passed to the foundation model. So the foundation model will end up, generating these results. And another input to these compilers are, gold labels. Okay. So for these input data here, I expect this response. Okay. For this input data here instance, I expect that other. So you need these gold labels here. all right? So you're gonna basically compare the generated results with the gold labels, and you're gonna estimate the error. Okay, suppose it's a classification task, okay? So for this configuration of my FMware, I generated these results, and only 60% of the instances are correct, okay? So I'm 60% correct and 40% wrong. That's my error estimator, okay? And I would come up with a score here. In this case, would be probably 60%. And I will use some heuristics to modify these hyperparameters here, okay? To get a new foundation modelware set of parameters, okay? And I will do this until I guess the best possible configuration. You realize this is all automatic, okay? There is no one kind of trying to adjust these knobs here, okay? We have a program actually adjusting these knobs until we find the best configuration of knobs for the whole program. All right? There is a lot of works trying to do similar things, okay? And one of the first works were Prompt Breeder by Google, I think. And they use a genetic algorithm to kind of mutate a population of task prompts, okay? And check which of these mutated prompts behaves the better, okay? The mutation operators, they basically try to modify the prompt somehow, okay? There is a prompt to modify the prompts, the meta prompts, okay? So here's an example, okay? These modifier prompts could be, so these mutation prompts could be something like this, you know? Say the instruction again in another way. Don't use any of the words in the original instruction. There is a good chap. So that will make, to generate a new prompt that is different from the previous one, and you use the the new prompt and check its performance again. And that goes over and over in a genetic algorithm type of thing. There is this evil prompt that also proposed some genetic operators to modify the prompts, okay? Very similar to what Prompt Breeder did. So here, there is even crossover, okay? So you get two prompt candidates, you kind of cross over them, you merge them somehow, okay? And then you can also apply mutations. So here is really genetic algorithm, okay? There is this automatic prompt engineer, which also, you know, propose some mutators of the prompt and applies a search algorithm again to kind of find the best of these prompts, okay? More recently, and this is gaining a lot of traction, there is this framework called DSPy, and the interesting thing here is that they not only give you the search algorithm and the mutators of the prompts, but they also propose a programming model where you can define the FMware as a pipeline of operations, okay? And then each step of this pipeline has its parameters, and the DSPy compiler tries then to, you know, modify these parameters and again try to find the best configuration of these parameters. The compiler by itself, the optimizer, works pretty much as I showed on that figure, okay? But the main contribution here is this programming model for you to represent your FMware program. There is SAML by Microsoft, which is a symbolic prompt program search. So it's very similar. It also propose a programmer representation, and then it applies a lot of mutations, not only in the prompts, but on the program by itself. Okay, so it's written in Python, and you use meta programming to kind of modify. This graph that you are seeing here, this DAG, it's actually the program, the representation, okay? So there is a lot of operations such as, you know, delete node, change format, and so on that it applies randomly and comes up with new programs. And these new programs are evaluated and the best configuration of the best program actually is returned as a result, okay? And even more recently, there are two works that are doing this. One is Prodigy, and the other is this TaxGrad, that they use a gradient descent as a metaphor to optimize prompts. Okay, so you know, They simulate this gradient descent approach to optimize prompts by doing a forward step that will use a mini batch of data. Those exactly what I showed there on that first figure, okay? And they use also a reflection prompt to generate gradients. So what are these gradients? They get a prompt, they pass the prompt to the foundation model, and the foundation model produces a result, okay? Now it asks the foundation model to reflect over that result. Why is this wrong given this prompt, okay? And then it will generate a critique, okay? A text criticized. Oh, this instance here is wrong because this, and that, okay? And then this is the gradient, okay? The critique by itself is the gradient, and this will be on the backward step, okay? We're gonna get this gradient, and I will ask again, modify the LLM, modify the prompt, having this critique in mind, okay? And then you will come up with a new prompt, but now considering why the first attempt was not correct, okay? And this is illustrated here in this figure, all right? So you do the forward pass, you have a prompt, you pass to the foundation model, the LLM, you get an output, you get this output and pass to another LLM that have a final output, okay? Now on the backward step, you're gonna use these self-reflection prompts. You're gonna ask the LLM to reflect why this was correct or why this was incorrect, okay? And this will be used as the gradient to kind of fix this output here. I will do the same. So this response can be improved by, okay, this is the gradient. This prompt can be improved by, and I will do the forward pass again, but first I will ask the LLM, consider these feedback, modify this prompt, and I will try everything again with the modified prompt. And I will try this many, many times until I hopefully get a better prompt at the end, okay? So these compilers still have a lot of challenges, okay? And I list 10 of these challenges here regarding, establishing quality programming constructs for representing these programs, okay? Consolidating the forms of compilation, because most of the compilers right now, they only try to optimize the prompts, but we have so many parameters in the programs by themselves to be optimized, okay? We also need to identify the set of most effective heuristics, so we need a lot of empirical work here to determine what these heuristics are and which one we should invest more. Okay, construct this set of gold labels. They are really necessary to this type of compiler here, okay? We can also assure the quality of the FMware application with this compiler. So when do we fail compilation, okay? Maybe the failing compilation is related to a certain amount of the instance of the gold labels failing, okay? We also need to reduce the cost and improve the efficiency of these compilers. They are very expensive to run right now, okay? They do multiple calls to the foundation models. Make compilation reproducible, okay? So you want to run the compiler multiple times and get the same result at the end. Enable these user-defined and multiple concurrent objectives to be optimized. Maybe you want to optimize for cost and speed at the same time. These compilers are not allowing these right now, okay? Improve the interoperability between these compilers. These compilers don't talk to each other right now, but we believe that at some point they should maybe have an intermediate representation or something like that. And finally, build community sharing platforms of these compilation traces such that they can be fed back to the compilers and the compilers improve themselves with this feedback, okay? That's everything I would like to talk today. I still have like 6 minutes for questions, and I would love to hear from you guys. Thank you.
Thank you. Thanks for the amazing presentation. We've got some questions over there.
Sorry. No, you go ahead.
So, hopefully a very quick question. So there's this, the whole interest in prompt engineering is if you think of it as fine-tuning, for example, as something that you prepend each time you complete a line and so forth, it sort of makes sense to make it reliable for new model, but then wouldn't the overfit on evaluation data sets? Or are there other tasks where it's not like prompting is not really unique to that particular task that you're doing, and it's not like doesn't even make sense to really do it, redo it for the next version of the model? So these are two slightly separate questions.
Yeah. So the question is, if we think that there is overfit, I think so. I personally think sometimes there is. You're really,
Especially if you do this compilation stuff, right?
especially if you do this compilation thing.
Right. So the second question is, are there like areas where this prompt engineering makes sense?
Sorry.
Other areas.
Yeah, so I mean, it seems like a lot of times prompt is very unique for a particular task. So why would you actually maintain it? Why would you actually do maintenance on it and make sure it runs on a new model? Because maybe you're never going to do the same task again ever.
Yeah. I think there might exist tasks like this, but the majority, I do believe that the majority know. Like, you're gonna evolve these models for many different reasons. Opting out data, fixing bugs, misclassifications and things like that, and you're gonna have to adapt the prompt very likely, just because it's gonna behave differently. So, I do think there are some tasks that are very specific, and you're gonna have very specific prompts, but some of them no. That's just my take. Sure, yes.
Observation, but what I would like to say is that if you integrate the prompt in a software, probably it will be used many times. And
Yeah, that's where I come from. Yes, exactly. Yeah.
My question is regarding evaluation. I'm trying to map it to what we had in machine learning, the approach we use. They have greedy search or search that to find the best parameter for each algorithm and then find the error rate and so on. Here, the thing is that the algorithm part is a blind box. And apart from that, we can change the various prompt. What's the best practice to say that this prompt is good enough based on which threshold we're gonna accept it, that not covering the go to overfitting 90%, 80%, or even if it's the average? Does it mean that one prompt is not enough? I mean that we always should consider the 5 top prompt, or in general, what's the best practice you suggest?
Sure. Yeah, I just to clarify this, I don't think overfitting it's gone. It is a problem. So again, I think one of the challenges that I mentioned is like these gold labels. They need to be representative. They need to be diverse, and so on, for us to at least minimize this problem. Okay. Now, in terms of evaluation, I think I do think we need to test multiple prompts and not report the best result, but actually a range. Okay, so especially when we're doing research, we should report like, I got results from here to here, right? Depending on the prompts that I was using. Now, when you're talking about building FMware, okay, so taking as a starting point that we're building a system, okay, then it's really on the developers to say, okay, this is the threshold of quality that I assume is the minimum, and anything below here, I will not put into production. And I do think that the compilers are very good at this, at outputting not only a compiled program, but also a range of these quality thresholds, okay? So during compilation, I saw instance, because this is exploring a huge search space, right? So during compilation, I saw, results from 0.5 to 0.8. So this is what the range of quality that you should expect. If the gold labels are representative and etc., you should expect to see after deployed, right? So, and you can decide, of course, always as, okay, 0.5 I do not accept, So I will have to find another configuration, or I would probably have to modify my program to behave better.
Consider this 0.5 as well in the final product, right?
I still think we're going to use the same old things that we have been using, right? Like defining based on requirements, on, you know, the domain. If the domain is very sensitive, you're going to have better quality assurance and so on.
Sure. I'm very excited. I have to say this. Your presentation was very organized, very informative. I really enjoyed
Thank you very much.
Thank you
I'm very
very
happy
much.
to hear that. Thank you.
Thank you for a great talk. So
Thank you.
I just had a question on what you would think of the following idea, right? So in some cases, you want the best possible performance, right? So I'm using an LLM in my business for a particular task, and I get the best performance on a particular configuration, and I go with it, right? And then that's one setting, and that seems more liberal. And then there's another setting where you're trying to write a paper and say, this particular prompt engineering gives you a certain kind of improvement. In the latter case, it seems like one should be more concerned about confidence intervals, right, or fragility, or whatever it is, to say that this particular configuration and all the variants of this configuration are better than some other thing that I'm saying I'm better than, right? So then, and this improvement is statistically significant, right? So it seems like there's possibly two different settings. I just wanted to get your take on that.
Completely agree. I thought about this many times. Yeah. And again, I honestly think these, not the compiler by itself, but this whole idea of exploring a search space and checking, look, things are now in a range of performance. Okay, I tried to generate code with my LLM, for example, and what I saw during this exploration of the search space was I got very bad results, but I also got very good results. For research, this is what we should be report nowadays, instead of just, oh, I found a prompt that it's good here, you know? So totally. And I think these compilers are they're implemented. They can already do that. So I think research-wise, we should be thinking more in terms of confidence intervals than anything else. Thanks. Yeah, very nice.
Okay. Thank you. Let's thank Filipe. I have to wrap up.
Thank
we
you.
have a break.
Thank you.